So it's a very great pleasure to introduce to you the Dean's distinguished lecturer for today, Mike Davis from Ohio State University, who's an old, very good friend of mine. And he's going to talk to us today on random graph products of finite groups. Random graph products of finite groups are rational duality groups.
Okay. So am I supposed to do something by looking at that, or is it just do it automatically? You're doing it. Okay, so I think I want to begin by, so first of all, this is joint work with a new colleague of mine, although I started this a couple of years ago when I was on sabbatical, named Matt Kale, who's actually combinatorialist. So this has something to do with random graphs and something to do with group cohomology. Basically, the rough summary of the talk was I heard him give a talk on his PhD thesis when I was in Princeton, and immediately it was very similar to some things I had been thinking about the cohomology of graph products, so I just combined the two things. But, and also I should apologize, I think some of you might have heard this talk before. So first of all, this is G, which is, this is the only time I can stand doing it. We just did it in paper as a graph, not a group. You can barely stand that. And usually the vertex set, we're just going to think of it as having n vertices, and we'll think of the first n integers are 1 to n. And now one thing, jump into it right away, one thing you can do with a graph, a simple graph, is you can make a simplicial complex out of that. So I'll call x sub g, so I call it the associated flag complex. Combinatorialists call it the associated clique complex. And it's a simplicial complex because they call, and so what it is it's I guess the largest simplicial complex which contains the graph as its one skeleton. Okay. I think that's right. In other words, what it is you take the same vertices, the same edges, and you fill in the simplex every time you see a complete subgraph. Okay, that's what the clique complex is. So it's a simplicial complex. So this is going to come up all along. Now let me tell you what a random graph is. So this is sometimes, I think, this has different names. Maybe somebody can tell me what, maybe Kyle can tell me what the official name is. I'm going to call it GNP. This is sometimes called the Erdos-Renyi model of a random graph. Sometimes it's called the Bernoulli graph. Sometimes it's called the binomial graph. I don't know what the official word is. The Bernoulli random graph.
There probably isn't an official word.
What?
I don't think there's an official name.
Erdos-Renyi maybe. But anyway, what it means is you look at the set of all graphs. You look at the, we're going to make it a probability space, but you look at the set of all graphs with n vertices. So you just fill in certain edges, and and then you attach a probability to a graph. What they say is you insert edges with uniform probability p. In other words, if you have so p is the probability that any edge occurs. Okay, so whatever p is, it's a half. You just flip a coin and put that edge in, or you don't, or whether it's heads or tails. So in other words, for a given graph, the probability of that graph occurring out of all possible graphs is p to the number of edges times 1 minus p to the number of things which aren't edges, which would be n over 2 minus the number of edges, something like that. That's the probability that's attached to any single graph. Okay. That's what a random graph is. And now, and basically the same probability space for the same thing. I'm going to let x and p be the flag count. Right away, I'm going to let that be the associated simplicial complex. Associated, each graph gives me a flag complex. And usually the way they think of p is often being as a function of n or something. And this is a big field, which I don't know that much about, but in fact, from our point of view, one of the first questions you might ask is, well, it turns out this is one of the first questions they ask, except they phrase it in different terminologies. What's the dimension of this flag complex? In other words, for them, they would say, what's the largest, I should have said with high probability. When does if it mentioned at least d means that there's a clique of order d plus 1 that occurs that it has to have at least one complete subgraph of d plus 1 vertices with high probability. So I should have said, we're going to use other abbreviations. WHP means with high probability, which means that as n goes to infinity, so we're going to talk about some property, like the graph, like something is d-dimensional, or the graph is connected or something, or say it holds WHP, means that as n goes to infinity, the probability, the set of graphs which it holds for, has probability 1. Means as n goes to infinity, probability goes to 1. Sometimes this is called AAAS, asymptotically, almost surely. I think that pretty much means the same thing. And other notation I'm going to use all along, I'm going to write f, just for this work, I'm going to write f is less than g. It's funny, less than g means that f is going to mean f is little o of g, which I remind you means f over g goes to 0. And I'm going to write f is considerably less than g. It really means that f times n to the epsilon for any small power of epsilon for g goes to 0. So it's really, f is less than, f over g is less than 1 over n to the epsilon. That's just the notation I'm going to use. Now, it turns out that if you ask this question, well, let me just phrase the result, then I'm going to say a word about it. What's the dimension of this? Here's one way to say it. So let's let d be an integer, be a positive integer. And then if p is, I guess, just say bigger than n to the minus 2 over d, and this is a funny lesson, less than minus 2 over d plus 1. So if you're in this range, then the fact is that with high probability, the dimension of this x and p is equal to d. So I thought, whatever that means this, it means that if it means, so the range of, so the things look like 1 over n squared, 1 over it's 1 over 2 to an integer, so 1 over 2 to the 2 is 1 over n, 1 over n to the 2/3, 1 over n to the 3/4, 1 over n to the 4/5, 1 over, no, what did I say, 3/4, 2/4 is 1/2, then 2/5, and then n to the 2/6 is 1/3. So here, we're saying that the dimension D is 1 in this range, it's 2 in this range, it's 3 here, 4 here, 5 here. It goes like that.
So prime P changes with n.
What?
The P will change with n as
I'm
well.
thinking of, I'm thinking of P as some sort of function of n that lies between those two powers. Basically, in fact, what you really say is that the cutoff for the dimension is this number, e to the n to the 1 over n to the 2 over d, and this is, I went to Matt Gale's course on random graph theory. This is like one of the first things you do. One of the few things I can understand. And it's based on, this is, if you think of the expected number, say, of clicks of order d plus 1. So the obvious calculation of this is that, so you have to pick d plus 1 vertices out of n, that's n choose d plus 1, and then each edge in there has to occur. So you're supposed to, by linearity of expectation or something, that's supposed to be the expected number of d-dimensional simplices. And if you think of P as a power of n, the power that makes this come out to be, I mean, this whole thing is roughly some power of n, and if you put in P is equal to minus n to the minus 2 over d, it comes out to be a constant, the same order as n to the 0 or something. So the real result is that when P is bigger than this, it has these d-dimensional simplices, and when P is less than it, it doesn't have d-dimensional simplices. So that's where it is. Okay, in fact, I'm going to be using some range like this all along, and D is always going to be the dimension of this Phi complex. Now, apparently the most famous result here is this theorem, I think in the late 50s, or I don't remember, of Gerdosh and Renn, which is one of the beginning theorems of this. And it says, it determines when this graph is connected. And the theorem says, it says something like this: if P is bigger than log n over n, and this, it's actually bigger, it's better than, it's a sharper threshold than what I said, then that implies GNP is with high probability connected. And if P is less than that, then that implies that GNP is not connected. Actually, this is a sharp threshold. You can really say if P is actually just strictly greater than a constant bigger than 1 times this, it's connected, and a constant bigger than 1 times, but a less than 1 times that, it's not connected. It's an even sharper threshold than these things with dimension.
And if it is equal?
What?
What if it is equal to this sequence?
What?
What if P equals to this sequence?
So if P equals this, or this plus a constant, then in fact, the way they prove this is they show that, let's say, the probability, if P is, say, something like, the way you prove this, I think if this is what you write to start with, if it's that plus maybe a constant, then if P is equal to that, then the probability that it's connected
There is something
is, so if I remember this right, it's something like, you can check if this makes these sentences right, it's something like e to the minus e to the minus c. Okay,
some number.
so some number between 0 and 1, depending on what c is. So when c goes to infinity, this is e to the minus infinity is e to the 0, so it's see, this is supposed to work out to either 1 or 0. So if c is going to plus infinity, this is e to the minus infinity, which is going to 0. So then e is going to
1
yeah, it should be.
from below, right, which is good.
Yeah, e to the 0 is 1, okay? And if it goes to plus infinity, if c is going to minus infinity, it's going to 0, okay? This is actually what they prove. This is the method of proving. And in fact, there's a whole big, they have other things. There's papers written called The Birth of the Giant Component and stuff. They think of what happens is P gets closer and closer to this, and some really interesting things happen. Like what happens is that as it gets close to that, they're developed basically some number of isolated vertices in just one big component, and then that's called the giant component, and then it just swallows it up. Anyway, so what Matt Kale did, one way to say what this is saying is it's saying that the, say, zeroth Betty number, or the zeroth reduced homology of G and P is equal to 0 for the pi probability. Notice that this thing is bigger than 1 over n. It's in that range in here. It's in the 2-dimensional range. So what Matt Gale did is prove the analog of this has investigated what happens for this random flag complex, what its homology is. And the answer comes out, he didn't have all of this in his thesis, but the best result is a paper which is on the archive. And it says this, so I'm in this range, maybe I'll make really less than, it's between minus 2 over d plus 1 and n to the minus 2 over d. Then the result is that the cohomology or homology of x with rational coefficients, put reduced there if you want, is concentrated in 1 degree, okay? Namely, in degree half the dimension. So it's only non-zero in the greatest integer less than d over 2, okay? Call them Macaulay complexes or something, okay? In his thesis, he actually did, you can ask what happens with integers, and the answer isn't completely known there, okay? What's known is that with integer coefficients, it vanishes above this degree, and that in fact for this value of p, it's d over 2 divided by 4 connected. So it doesn't become simply connected until d equals 6.
Am I going to choose it? I thought Cohen-Macaulay is expected to be non-zero in the top dimension, right?
But yeah.
But you said Cohen-Macaulay.
I did say that to try to. It's all concentrated in 1 dimension. It's like, in fact, the way I was, at some point I wanted to make the remark that these things are like thickened Cohen-Macaulay complexes. Because there's the same property that holds for links in Cohen-Macaulay. It's not the top dimension, it's the middle dimension. Right, so if you think of it as some sticking Cohen-Macaulay complex. Okay. Anyway, there are statements with integral coefficients, but it's not, and it could happen that maybe this is, with integral coefficients, maybe it's all concentrated in this degree. But that's not known. In fact, that has some bearing on what I'm going to. It's known above that and except in this range between basically the dimension over 2 and dimension over 4 is where it could be non-zero. Okay, so the current proof of this uses things about, I don't think I'm going to have time to say anything about the proof, but it uses business about the combinatorial Laplacian and the spectral gap of that. And it's based on ideas of Garland a long time ago about proving things have property G, and that Baldwin and Shrienkowski used. Anyway, so anyway, I think this is it's a beautiful, actually, topologist seems like a natural thing that we should have asked. I don't think they really did do it in random graph theory. They did a bunch of other more complicated stuff, but it's a direct general, it's the next step after Erdos-Renyi in some sense. Now when I heard that, I actually knew what to do with it, because I had been looking at these things, Coxeter groups and Arden groups, and I've been computing their group cohomology in terms of this flag complex. So I knew what to do. So let me do that now. So the general situation, I want to talk about a graph products of groups. So again, I'm given a graph, and I have a sequence of groups, gamma I, say indexed by the natural numbers or indexed by the vertex set will be n and n. And then the graph product, which this is all from the paper. Didn't come up with enough G's once we put G for graph. So G is going to be the graph product. So the definition of this is that you take the free product of the gamma i's and you divide by the relation. You divide by the normal subgroup, which is basically you set gamma I and you make gamma I and gamma j commute whenever I and j are in edge. So most of the time you can think of gamma I as being a fixed group. For example, if gamma I is the cyclic group of order 2, this is what's called G is right-angled Coxeter group. G is the right-angled Coxeter group associated to the graph. Which is just defined by this relation. If gamma I is equal to the infinite cyclic group, then G is what's called the right-angled Arden group. Associated to the right-angled Arden group, yeah. Okay. So I want to tell you something about how to make a K pi 1 or contractible space which these gamma i's act on. So basically, in fact, I should say, so these are sort of two different cases, and what happens is that we've done sort of calculations of these group cohomology, and there's sort of two different answers, answers depending on whether all the gamma i's are finite or whether they're all infinite. Okay, and the first one I did in the paper with Mari, Anishkewicz, Oaken, and Meyer, and the second one I did in the paper was more just a straight spectral sequence argument I did in the paper with Oaken. Well, let me tell you one way to describe what the K-pi-1s are. So there's this general construction that these guys have been, Fred Cohen and these people have been talking about, Tony Berry and so I want to tell you something that's called the polyhedral product. So suppose I'm given just some collection of spaces, AI, BI, where I is in the vertex set of is indexing my vertices of my graph, and I have some simplicial complex with the same vertex set. Vertices of X are this n. And then I'm going to define something, I'm going to call it Zx, I don't know, of AI, BI, or it might just be one. It's going to be a subset of the product of the AIs. And what is it? So a point in here, I'll say is x, and its coordinates are say xi. So if I have a point in the product, I'll write sigma of x to be the set of I, the set of indices I, such that the I coordinate has support in AI, or in other words, it lies in AI minus BI.
AI and BI just spaces?
They're just spaces for a minute. Yeah.
So is BI a subset of AI?
Yeah, BI is a subset of AI, yeah.
What's the punctuation between AI and BI, the very last thing? The very last, bottom right hand corner of your board. So AI, what's between?
AI minus BI.
Minus, sorry.
So, okay, we'll see in a second. So the coordinates can always lie in BI, but, so the definition of this Z sub X is it's supposed to be the set of X in the product of the AIs such that the sigma of X is the vertex set of a simplex, including the empty simplex. So in other words, if you like, what this means is, one way to think of this is basically for each simplex, you take a product of the AIs, where the I's are the vertices of the simplex, and then you cross it with the BJ's, where J is not a vertex of the simplex, except you put them in the natural order, then you glue those together. It's made out of pieces like that. And included in the empty set corresponds to the piece where all those factors are BJ's. I'll give you an example. So in fact, one example, which it turns out, for example, that if AI BI is the K-pi-1, if AI is a B gamma I, and BI is just a point, then I won't prove this one, but then this DX B gamma I star I is the K-pi-1. This is, in fact, if you do this, for example, if each of these is Z, this is the usual construction of a K-pi-1 for an argument group. But this is a classifying space for the graph product.
So in the product, the first thing is AI or AI minus BI?
I think I just mean AI. give the example I know for sure, and we'll see if it's right. So the example I've been doing for years with this comes up in the case of Coxeter groups. If you let AI just be the interval from -1 to 1, and BI to be plus or minus 1. Now, if you think about drawing this, you think, say, x, say we have 3 vertices, and say x might be, this is the one I always draw, 1, 2, 3, something like that. 3 vertices and 1 edge. So the whole thing is supposed to be a subcomplex of the 3-dimensional cube. Now, the fact that I have the fact that the empty simplex isn't there is saying that all the vertices of the cube are in there. The fact that these 3 vertices are in there says that in every direction, you have the whole 1 skeleton of the cube. And this 1, 2 being there means that you basically have all the things that look like this simplex is going to correspond to the top and the bottom faces. Okay. So this is an example. This is an example of really a picture for the next example. Okay. This is an example that has to do with the right-angled Coxeter group picture. But in fact, let me just say a generalization of this. The reason this is that the Z2 cross Z2 cross Z2 acts on this picture, and the group of lifts is the right angle. It's not simply connected. So the next example, which I'm really the main example I'm interested in, is let's suppose that each of these gamma i's is a finite group, and I'm going to let AI, BI be, as in this case, the cone on gamma I, comma gamma I. So if gamma I is equal to Z2, I'm thinking of, if it's plus or minus 1, I'm thinking of that case over there. Okay? And in this case, then I can take this Zx of this thing, and I can take it's not simply connected, for example, it's not simply connected in that picture, and I can take its universal cover. And the claim is that this is, so the claim is that this is contractible, at least if X is a Flag complex, if and only if X is a Flag complex. And the graph product acts on it, possibly not freely, but with finite stabilizers. So if before I take the universal cover, I have the product of the gamma i's, certainly acts on the product of the cones on the gamma i's, and it leaves and it acts on the Z sub x, and it just follows from basically from the definition of graph product is the universal property that it has is that the G acts. In fact, it is the group of lifts of this action. And this action to the universal cover. So this is partly how I don't know, be necessary to do this, but I'm doing it. So in other words, i.e., the z tilde sub x is equal to what we would call, well, it's a contractible space. The graph product acts on it as finite isotropy groups, and their fixed point sets are contractible. So E, it's the classifying space for finite actions for this graph product. This is independent about what, I mean, this the only place I'm using finite is with the, say it's E under bar 2. Okay, so, just trying to think that I have enough time. Okay, so I should also say that if you take the quotient space of these actions, you get what's called the fundamental chamber for one of these things. So in fact, it's just this z sub x applied to the pair unit interval comma 1 point, and this is and in fact, in the case x is a flag complex. Okay, so this is this quotient space. I often call this k or something, but what it really is, I'll just say a little. I won't say much about it. Is it's homeomorphic to the cone. It's easy to see that it's homeomorphic to the cone on x, when x is a flag complex. Well, in any case, it's homeomorphic to the cone on x. And what happens is we think of this as sort of a fundamental domain for the action. I think I'm just going to leave it like that. But this is where the connection to these formulas come in. So one formula, the theorem. So this is a theorem that I did for a long time ago for Coxeter groups, for right-angled Coxeter groups, and eventually it turns out that more or less the same formula is true for the graph product of any collection of finite groups. This is Davis, Demar, Januszkiewicz, John Meyer, and Boris Okin. So we're assuming that, say, all the gamma i's are finite. This is in a paper that we called, okay, so what are we interested in calculating here? So why am I talking about these things? So one reason is that if you calculate, say, the cohomology of this z tilde x or something with compact supports, this is the same as the cohomology of the group with group ring coefficients. So this is something that you might want to calculate, and we did calculate this in a paper called The Compactly Supported Cohomology of Buildings. And why would you want to know this? Well, for example, so why would you want to know something like that? For example, one reason is it tells you the number of ends of this space, tells you the number of ends of the group. It means the number of, if you take that larger and larger compact sets, the number of components that you have. So it says the number of ends of G is basically the rank of this H1, I guess plus 1. If this is, what? If this comes out 0, that means it's 1 end. Yeah.
Is that integral or rational coefficient?
No, either.
Well,
Okay, rational.
top of their one.
This is true over the integers, it turns out, but it's an exercise in Ken Brown's book. Even though there's finite stabilizers, it's still true over. It's like a virtual primary duality, so this is Z. Okay, so suppose all these gamma i's are finite, then our formula was something like this. It said the cohomology of the thing we're interested in, G, I can't say with ZG coefficients or with rational coefficients. So this is the cohomology, compactly supported cohomology of this space. It's a direct sum over the simplices of over the simplices in the Flag complex associated to the graph, including the empty simplex of things that look like this. The cohomology of the cone on X, which is contractible, but its relative cohomology of this comma X minus a simplex, the complement of a closed simplex in there. See, this is exactly the way we did it, but this comes from thinking of fundamental domains, where one copy of this was a fundamental domain, and this was sort of a union of walls of a fundamental domain. And then its tensor some free abelian group. I'll just write A sigma or something. But this is some specific free abelian group which I don't want to describe. And it has an action on it. Usually infinitely generated. But it says up to, usually the cohomology will either be 0 or infinitely generated, but when it's 0 or not is determined by this Flag complex X, or maybe the complement of a simplex in this Flag complex X. So, so that's what we did in the one paper. I think I'll just end up skipping. It turned out if you do this where all these gamma i's are infinite, you also get a formula for the cohomology with group ring coefficients. It's also a sum over all the simplices, but the terms which occur are the links of the have to do with the links of the simplex. The cone on the link of a simplex, comma the link of a simplex, and then having something to do with the cohomology of the individual pieces, of the individual groups, and their products. I was going to write that down, but I think it would just degenerate. So this is a formula. Originally I did this for Coxeter groups, and it wasn't so easy. Basically, I think we had John Meyer and I had a false proof of this in a paper that you refereed. That you admitted to me once.
Referees are completely anonymous, nobody knows who they are.
But anyway, it was a true theorem, which we eventually fixed up. Okay. Okay, so now we can just combine this with, I think I can just say what the results are now. So I can combine this with do I have anything else I want to say in here? Okay, so the theorem in our paper says this. So we're in this, between these two thresholds. And then, with high probability, you can say the following. And we're assuming that all the gamma i's are finite. So this goes back to the title of my talk. So I guess the basic result is that, well, the first thing I should say is that the cohomology of this graph product, let's say, coefficients in the rational group ring, is concentrated in one dimension. Is concentrated in degree, well, it's not d over 2, it's d over 2 plus 1. Okay, so the shift in the 1 came from the fact that I'm looking at relative cohomology here. Oh yeah, I forgot to say, so one new ingredient from random graphs in our, I'll say that next, but when sigma is equal to the empty set, we get that, but I also need a statement for all simplices, okay? Yeah, I forgot the main theorem we actually proved, but these are the consequences. I'll come back to that at the end. So, in particular, you can say, you can deduce various things about these. So in other words, this G is, if you like, G is the random graph product. Graph product corresponding to a random graph. Well, the virtual cohomological dimension of G, well, its cohomological dimension over the rationals is d over 2 plus 1. Its actual virtual cohomological dimension over the integers is either d over 2 plus 1, or it might be d over 2 plus 2. The d over 2 plus 2 could occur if the integral homology of this x in the top, in dimension, in degree of d over 2 has a portion in it, and that would shift it up 1 degree in cohomology by the universal coefficient. And you can say what the number of n's is here. And say, so I guess it's, if d is at least 2, if d is equal to 1, the number of n's is 1. It is infinity, and if d is bigger than or equal to 2, the number of n's is equal to 1. And so the consequence of another reason for studying this group cohomology is that, for example, to say that a group is a Poincare duality group, one way to say it is that it only has this homology concentrated in 1 degree, and that degree, and it's only equal to z in that degree. It's infinite cyclic. And motivated by that, Vieri and Ekman had other examples, but they said if you had a group, so their definition, so I'll just say, maybe you say this and then it's the definition, is that G is a rational duality group. A formal dimension. D over 2 plus 1. What that means, that just means that all the cohomology is concentrated in 1 dimension. If you set it over the integers, it would mean it's all torsion free and concentrated in 1 dimension. So it turns out so that was the title of my talk. All these random graph products of finite groups are these it's a weird, strange fact. They all turn out to be these rational duality groups. So I should have said, maybe I'll just say, what I left out was the theorem that we had to prove in here with Kale was that Davis and Kale was that his results for X, all for X and P, are also true if you subtract any also hold for the complement of X, for X minus any simplex. That's one, and I'm running, the other thing, if I had done these things about links, another fact is that is that we had to prove that for any simplex sigma, whose dimension is less than half the dimension, that the homology of the cone on the link of sigma, this is from the formula I didn't really write down, cone on the link of sigma is 0 for something like in degrees less than d over 2, then I want to put in something like minus 2 times the dimension of sigma plus 1. Okay, something like that, in low degrees. This is what we needed to prove results about infinite groups. Maybe I'll just state what happens. The cleanest case is for right-angled Artin groups. I'll just state that. So if we're in the case where all gammas are equal to z, so this is the random right-angled Artin group case, then you don't get exactly, because of the fact that we have these different formulas, which I didn't tell you, you don't get exactly the same conditions, but what you do get is you get that it's, you get that the cohomology of, first of all, let me write some things that are known. First of all, the cohomological dimension of this Artin group is the dimension of the complex. And secondly, you don't get that it's all concentrated in one dimension, but what you get is that the cohomology with group ring coefficients is equal to 0 in dimensions less than the middle dimension. Above the middle dimension, it can also be non-zero. And it's non, and you get that, it's you can compute it in terms of it's non-zero in dimension d over 2. You also get things like, maybe I'll say one last thing, just the L2 Betty number. Of this group is not equal to 0, only in the middle dimension. Only in dimension k equals d over 2 plus 1, and in which case that L2 Betty number of the group is the same as the dimension of the L2 Betty number of the complex. That comes out of a paper that Ian Murray and I wrote, but anyway. So I just wanted to say there's other results for infinite groups. They all are something like this. The cleanest case is where all the groups are Z, in which case it just says that, but in general, all it's going to say is that it's connected up to the middle dimension. It's chronologically connected up to the middle dimension, but after that, in fact, not. It has homology all the way up to the top dimension.
questions for Mike?
In your theorem on this blackboard, I was saying, I mean, this is all about the randomly with high probability and so on. I mean, there's no mention of.
Yeah, I should have, that had the same hypothesis as the
Same
others.
hypothesis, yeah.
Yeah. P is in that range, the dimension of D.
What about in that theorem if, instead of all being Z, if they're all, say, virtually cyclic, infinite virtually cyclic groups, but variable ones instead of Z, they could be, would you get the same sort of result?
And you just took the graph product?
You know, like infinite dihedral and infinite cyclic.
Well, first of all, if they're all infinite dihedral, I think it's not obvious, but it's not obvious from the definition. But in fact, I think then it's commensurable. Has up to the group of finite index. It's the same as the right-angled Artin group. And I think it seems to me if all these gamma i's are I didn't think about that, but if they're all virtually cyclic, if they're all virtually cyclic, I'm pretty sure. Well, this might be slightly. If they're all virtually cyclic, this is this thing is certainly true. This thing is certainly true. All of these things will all be true. Even if they were virtually abelian, the only difference is that the cohomological dimension would go up.
What about if you put, instead of the infinite cyclic, say a free group or something, does that get really bad then?
So the real result is that free groups are probably okay too, but in general, the real result is it has to do with the group ring cohomology of the factors. Okay, so the infinite cyclic or free groups, it's all concentrated in dimension 1. But if you said something else, it gets screwed up. The real result is that the answer is something like it's a direct sum over the simplices. So something looks like a cohomology. It looks like, say, dimension m. It looks like the cohomology of these links of these simplices shifted by one dimension. And then tensor the cohomology of these factors and products of these finite products of these factors over simplices. Okay? So it looks like terms that look like the cohomology of, say, these things I call, this shouldn't be I. K and L, of these gamma i's, again, tensored up with some group ring coefficients. So if these were all virtually cyclic, then these things would all look like, power z to some power. They would be like the torus, and they would just have homology in 1 degree that would be shifting things up. Works perfectly okay. If these were just randomly, and if they were free groups, it would also, I guess this result would also be true. If they were some other fundamental groups of aspherical manifolds, then you have some kind of other terms in there, other dimensions.
Are there any other questions? We have another talk soon.